will be recorded. Yeah, since some of them are having tuition today, okay, so I will be recording it and then I'll be uploading to YouTube. Okay, so if you're not able to catch, you can always refer to the link as well. Okay, if not, what I aim to do today is actually to go through these 4 things. Yeah, charge current, conventional current, electron flow, and potential difference. Okay, but we'll see how it goes. Okay, I won't take too long. Okay, because I know it's quite late. Okay, but yeah, give me about 30 to 45 minutes. Yeah, okay. So I think we can start. Okay, yeah, just nice. We have just for some of us we have finished static. Okay, and for some of us we are in the middle of it. But I think we are good enough to actually answer this question. Okay, so the key difference between conductor and insulator. Okay, so while they both have electrons, what's the key difference between these two? Anyone?
In conductor, the electrons can move inside, and insulator is only around.
Okay, great. Okay, so conductors have free mobile electrons that are able to move inside. Okay, and that is the reason why conductors will be used to make wires in this chapter. Okay, because we need the electron in the wire to move. If the electrons inside the wire cannot move, we cannot have electricity. Okay, so basically, if electrons are represented by balls, okay, this is how a conductor one will look like. Whereas remember in insulator, while you have free electrons, they are on the surface. Okay, and my electricity cannot flow. Okay, so what I need is electricity to flow, and for electricity to flow, okay, in this chapter, what I need, right, is for electrons to move. Okay, so if the electrons are not able to move, okay, then clearly I will not be able to produce electricity. Okay, that is why I start off with this entire idea of conductor and insulator. So while insulator have electrons, they are not mobile. Okay, so both have electrons, okay, and both have the ability to lose or gain electrons. It's just that for conductors, right, their electrons can move inside the conductor. Okay, and that's very important. Okay, now in the previous chapter when we deal with static, okay, we actually talk a bit about atoms, okay, and the atomic structure. All right, for those who just came in, I'm doing the new notes, so you can take out the new notes. Okay, so let me introduce you all. This SI unit is called charge. Okay, so you heard of this thing before called charge, right? And then in the previous chapter we always talk about negative charge and positive charge, right? So exactly what is this charge that how do we actually define this charge? Okay, so charge, right, is actually a quantity. Okay, so the quantity name here that we are dealing with now is called, let me change to another ink that is thinner. Okay, sorry. Okay, so the quantity that we are dealing with, okay, just like all other physics chapter, there is always a quantity like maybe wavelength, maybe time, maybe displacement. Okay, there's quite a number of quantity. Okay, the quantity that we are dealing with today is the first quantity is known as charge. Okay, this quantity has a SI unit called Coulomb. Sorry, the U and O should be swapped. Wait, let me just double check them. Okay, so Coulomb, and the symbol for Coulomb is C. Okay, so what is charge? Charge is a characteristic of an electron. Okay, and just to give you a rough idea, right? So one electron has a charge of 1.6 times 10 to the power of minus 19 Coulomb. That means it's able to create an electric field of somewhat around this strength, okay, at the center of it. Okay, so this is the entire idea of like charge. Okay, it's, they are kind of telling you how much electric field you can create. Okay, obviously the stronger your charge, okay, the more electric field you can create. Yeah, the stronger.
So that's one electron has a charge of 1.6 times 10 power negative 19.
Coulomb, yes. Okay.
For one, right? For one only.
For one electron. This is for one electron.
Okay.
This data, right? Data given in exam, so no need to memorize. Okay.
Mr. Bro, can you report that to?
I recorded. Yeah. Okay. Now, so one electron has a charge of 1.6 times 10 to the power minus 19 coulomb. Okay. That's really very small. Okay. In this chapter we'll be using coulomb quite frequently. So let me define for you. 1 coulomb, right, will therefore refer to how many electrons? So it'll be 1 divided by 1.6 times 10 to the power minus 19, which is equals to, can someone calculate this for me please? I think 6.25 times 10 minus 8 times 10 18, but I just want to confirm. Anyone did this calculation?
6.25 times 10 to the power 18.
Okay, so 6 point, thanks. That means 1 coulomb has this amount of electrons. Okay. So every time we say, oh, this thing is 1 coulomb, we are saying that okay, that part of the wire. So we say this part of the wire is 1 coulomb. It's actually 6.25 times 10 to the power minus times 10 to the power 18 electrons. Okay. Remember in static we say the negative charges move and the positive charges, they don't move, right? So we say that electrons is flowing to the left or flowing to the right, etc. Now, when we say one negative charge move, we are basically saying that 6.25 times 10 to the power 18 electrons are moving. Okay, so that's the idea of like one charge, 1 coulomb of charge, right, is this amount of electron, which is like more than a billion. Yeah, it's a billion times a billion number of electrons. Okay. Okay, so y'all have any question regarding this, like the idea of charge? So basically charge is charge is a quantity that defines the strength of electric field. Okay, so basically if your charge is higher, your electric field is stronger. If your charge is lower, your electric field is weaker. Okay, interestingly because this electron, the charge is negative. Okay, so this is just for y'all to know. Okay, 1 proton is equals to positive 1.6 times 10 to the power minus 19 coulomb. Okay, so it's the same in terms of magnitude. Okay, but they are different in terms of sign. So this is positive, this is negative. Right? Okay, so with this I think I can move on. Anyone got any question? You have like 10 seconds to raise any question if you have. Okay, if not, we'll move on. Okay, I'll go through this in class. Okay, yeah, so let's move on to current. Okay, so with the idea of charge, okay, now we can talk about current. Current, right, is known as the rate of flow of charges. Okay, now in a closed circuit, basically current, right, is how fast or how slow the electrons are moving. Okay, remember 1 coulomb is like a billion number of electrons. Okay, so I'm just going to talk about electrons and charge quite freely. Okay, yeah, just remember this conversion. Okay, so whenever I say 1 coulomb, I really mean 1 coulomb, like 1 billion electrons. All right. Okay, so the rate of flow of charges is basically the definition of current. Okay, and this is defined as current equals to Q over T. Oh, by the way, the symbol for charge is Q. Okay, just like the symbol for length is L and the SI unit is meter. Okay. Okay, so the symbol for charge is Q, and the SI unit for charge is Coulomb. Alright, therefore we have this introduction to current. The symbol for current is I. Okay, the symbol for Q is known as charge, and the symbol for T is known as time. Now, of course, this is in seconds, this is in Coulomb, and the SI unit for current is A. Okay, now current is a scalar unit, that means there's no positive or negative. Okay, the SI unit is ampere, okay, known as A. And maybe you should write here the symbol for current is I. Okay, so while we have this is the formal definition, I equals to Q over T, it is easier to remember Q equals to IT. Yeah, because there's no fraction. Okay, so this is easier to remember, like quite intelligent teacher. Okay, then maybe you can think of me. Then quite intelligent teacher, right? Okay, so yeah, you can think of me. Then you can remember the formula. Okay, so Q equal IT. Or you can think of quite irritating teacher. Yeah, same lah. Okay, so this is the formula. Okay, gonna not going to, there's no practice. Okay, we will practice in class. Okay, now I just want to just pass on the info to you so that the next lesson we can actually try to apply this formula. All right. Okay, anyone got issue with the formula? Okay, so a very simple question, okay, will be calculate current if 1 coulomb of charge passes through a bulb every 2 seconds. Okay, so you just need to apply the formula. So the current equals to Q over T, which is basically 1 over 2. So current is 0.5 ampere. Alright, so they ask you to calculate current of if 1 coulomb of charge passes through a bulb every 2 seconds. Okay, that means in this light bulb, every 2 seconds you have 1 billion electrons going through it. Then the rate of flow is just Q equals to IT, just apply the formula. Then I equals to Q over T, which is 1 over 2, which is 0.5. Okay, it's quite straightforward for these kind of questions. Okay, let me move on now. Anyone need time to copy or anything? Okay, so this is how I want you to view okay, this is how I want you to view the entire idea of DC circuit. Okay, basically your current, your voltage, and your resistance can be illustrated using this analogy over here. Okay, so can everyone see this screen? Can yeah, I don't know, Zhen Yang can see, or anyone else? Can okay, so now over here what we have, right, is an illustration of current. Okay, so for current, it's about the water flow. All right, and then there's one thing I want to mention about this illustration. I need you all to imagine that the water flow will remain the same even though it goes down. Okay, so this is something that we have to assume. Okay, so we assume that the water flow is the same. Okay, so basically what is current here, right, is a number of water particles passing through a section in a certain time. All right, so maybe over here, okay, maybe there's like a billion number of water particles passing through here every second. So using the formula, we can actually calculate our current. Okay, so you realize that current will flow if there's a potential difference. Okay, so remember what is gravitational potential energy? Alright, so let's say I put a ball here and the water is flowing. Naturally the ball will go down, right? Okay, however the ball here nearer to the tree, okay, let me see if I can on the whiteboard. And then no, I can't. Okay, so if you all can see the tree and the guy here fishing, okay, yeah, over here. Okay, so you can see the tree and the guy fishing, right? Over here, we'll call this our starting point. Okay, you'll realize that at this point, okay, the potential difference is the highest. So because it's the highest, okay, we say that GP is like the maximum here. Okay, whereas over here, okay, at the bottom part, you realize that the current is the lowest. Okay, that's because, oh, sorry, you realize that over here the GP is the highest, and at the bottom part the GP is the lowest. Okay, sorry, my mistake. Okay, the current should flow the same because we assume that the water flow rate is the same. Okay, so let me just illustrate this over here. Okay, can you all turn to the content page, right? Then I want you to draw this illustration out. Okay, because we are going to use it quite a number of times. Okay, I think it's good for you all to draw it out. Okay, so yeah, maybe just draw out a certain hue. Okay, please use a ruler, then it won't be so messy. Okay, just need to draw something like this. Alright, then we are able to illustrate current over here. Okay, so current will just be the water flow. Now current here will be determined by the water flow. Okay, and then we need an assumption. The assumption is this, that the water speed remains constant throughout. Okay, so far okay, this analogy okay. So basically it's just the water flow. That's how we see current. Okay, the next thing we are going to learn is about energy. Okay, so what allows the current to flow. Okay, that will be what we'll be studying next, which is known as potential. Okay, so at this point I hope everyone's okay. Okay, so let me move on. Okay, so the next thing we will learn is potential. Now I don't think it is very new to you all, this word potential. So if you all can recall, we just learned it recently only. Okay, potential is quite similar to the entire idea of gravitational potential energy. Okay, and then we'll look at it in terms of that. Okay, so over here, this portion of water has high GPE, whereas in fact it's not even high. At this point is the highest, right, because of its height. And then over here, okay, it is the lowest GP. Okay, so we'll use this idea of GP, right, to help us translate this idea into potential difference or voltage in this chapter. Okay, so shortly I'll be talking about voltage, and then we'll come back here to talk about GP again. Okay, so just quickly, from point 1 to point 2, you'll realize that the water, okay, is losing GP. So from 1 to 2, water loses GP, right? Okay, so I think we can stop here, and then we can move on to the idea of potential difference. Okay, so this is our current illustration. We'll continue adding on to this illustration every time I finish one concept. Okay, so right now I have finished the concept of current, which is basically the water flow, which will basically, the speed will remain constant. Okay, so let me move on to the next part. Okay, yeah. Okay, so let me introduce you all to the next quantity that I want to do today. The quantity is known as voltage. Now, the entire idea of voltage, right? Voltage is defined as the work done per unit charge. Now work done would mean the energy given out, right? Okay, that means every charge has a certain amount of energy, and voltage, right, is talking about how much energy is given out by a certain charge. Alright, so let's say I have a charge passing through a light bulb. Okay, that energy will be given out. How you know energy is given out? Because electrical energy is being converted to light energy, and then you see the light bulb lighting up. That's like the energy given out. Okay, so in that case, you'll realize that work is being done, and if work is being done, there must be a voltage somewhere. Okay, so same thing, this is a scalar, and the symbol for voltage is V. Alright, the SI unit is volts, okay, which is also V, and the formula is V equals to work done over charge. Okay, so this is charge, which has the SI unit coulomb. This work done, which is W, and this is volts, which is V. Okay, so voltage is about the energy being used by each charge. Okay, okay with this?
I thought the SI unit is volt, not volts.
Okay, sure, yeah.
But is it like with an S or without?
No S, no S, yeah, you're right. Okay, so far okay.
So what's the scalar?
Scalar means no direction, only magnitude, only number. That means there's no positive or negative vote lah.
How come? So it's only positive, don't have the negative sign.
Don't have, because it's the work done per unit charge. It's kind of like energy like that. Energy also don't have positive or negative, right? Yeah.
It's only got positive, don't have the negative.
Don't have negative, yeah. If got negative, it means something else. Maybe it's a lost. Yeah. So that one we will talk about in 2 chapters later.
Okay.
Okay, but it is really a scalar unit. Alright. So apart from that, everyone okay with the equation?
Same.
Yeah.
So why work then like the energy given out?
Remember what is work done? Force and distance, right? Then remember I proved for you all that work done is also mgh. It is also half mv squared.
Yeah.
So basically work done is a form of energy. Okay, so work done is defined as the amount of work being done by an object. So if that's the idea of work done, then voltage is just talking about how much energy is being given out by a singular charge. Okay, so it's the energy given out by a charge. That means if the charge had 10 joules of energy, so 1 coulomb of charge had 10 joules of energy. By the way, remember 1 coulomb is 1 billion electrons. So 1 billion electrons has 10 joules of energy. Okay, so if we say the voltage is 10, it means that it's constantly giving 10 joules of energy to this amount of electrons, or we are saying that this amount of electron is constantly giving out 10 joules of energy. Okay, yeah, in fact I think, can you write here energy given out or taken in? Okay, so there are 2 forms. One must be so for the electrons in the wire, right, they'll be actually giving out energy. Okay, for the electrons inside the battery, they'll be actually taking in energy. Okay, so that's how it works out. Okay, later in the illustration and some video, I'll show you all better what I'm talking about. Okay, but with the idea of introduction to voltage, let us go back to the illustration here. Okay, so potential, okay, will be related to the height of water. Okay, I want you all to see this illustration. first, okay, and then try to relate it to the idea of current and voltage. Okay, so remember current is water flow, and then we assume that the speed of water is the same throughout. Okay, so in this illustration, right, the water flow is the same throughout. Okay, the water flow will change if suddenly instead of this path here, the water flow change into two paths. Then there will be lesser amount of water in these two areas. Okay, but however we are not doing that yet. Okay, we are just assuming that the water flow is constant throughout. So there's one single stream, the water does not split path, the water flow will be constant throughout. Okay, we note that point number 1 has the highest GP, and we note that point number 2 has the lowest GP. Okay, so it's the same as potential. Okay, so basically this amount, okay, of charge, right, will continue to flow, and as it flows it will start to lose energy. So as it goes from here to here, it will lose some energy. Okay, and as it goes from here all the way down to this point, it will continue to lose energy. Now this is the idea of volts. Okay, so what is happening is that if it's flat, right, it's basically the wire. Okay, so when it's going along the wire, it's not going to lose energy. Okay, but when it's going down, it could be because of a bulb. Okay, so the bulb takes in energy. Okay, so the charge here, right, has to give energy to the bulb. So as it moves across the bulb, right, it's going to lose energy, and then it ends up here. It continues moving along the wire. Okay, so as it continues to move along the wire, sorry, let me take away the red dots. As it continues to move along the wire, the energy stays the same. Okay, then it goes through another bulb. All right, okay, so it loses energy, and then it continues to flow. Okay, even though at this point it has zero energy. Okay, this is not just lowest GP. If you remember, this will be GP equals to 0 joules. Right, okay, so the GP at this point, at point number 2, is the 0 joules, and it's the same over here. Okay, by here I mean here. Okay, this region here, right? Okay, we can say that the charge potential is 0 volt. That means remember the idea of volt, right, is here, work done per unit charge. Okay, so it's the amount of work that can be done by a charge. Okay, so when I say that the charge potential is 0 volt, what I'm trying to tell you is that at point number 2, at the lowest point of this entire hill, right, or this waterfall or whatever it is, okay, the charge potential here is 0 volt. That means the charge at this yellow color region is not able to do work anymore. So in order for them to do work now, okay, they have to continue flowing into a water pump. Okay, I'm not going to draw the water pump. We don't need to go to the idea of water pump. Okay, but it can go into, you don't have to draw this. Okay, let me just illustrate it here. Okay, I will explain again in class. Okay, so basically the yellow region, the charge at the yellow region has 0 potential. That means it's not able to do work anymore. Now in order for them to do work again, right, they need to go into water pump. The water pump will actually push them upwards. Okay, and as it pushes it upwards, it flows into here. Okay, and then once again the water is able to flow downwards. Okay, then the entire cycle will repeat itself. Okay, so there will be a water pump to bring the water up, and then it will actually push the water along the same height. Okay, so that the energy used is 0 joules. Alright, let me just show you all a simple animation over here. Okay, so this is something like how the electrons will flow. Yeah, over here. So you see, this is not force, by the way. Okay, don't think of this as force. Okay, this is basically the energy given to the energy that the battery will give to each electron. Okay, so can consider the red balls as either electrons or charge. Okay, but if you think of it as charge, right, remember it's a lot of electrons. Okay, so anyway, what happened is that when the electrons are used, they will actually go down. Okay, that means the potential energy has dropped. Then it will continue flowing at the same height, and then as it flows in the battery gives it enough energy to bring it upwards, and then it will continue flowing. And then it goes to the light bulb, energy is used, it will go down, okay, and then it will continue flowing at the same height. So no change in energy. Then goes up to the battery again, gain in potential energy, go towards the light bulb, uses energy, drop in potential energy, and then yeah, this entire cycle will continue. Okay.
So I want to ask something.
Yeah.
When it's dropped down, right? So there's 0 volt. How can it keep flowing? It just follow the current, is it?
Okay. So you can think of it as 0 volt, as in zero potential energy, but it doesn't mean that it does not have kinetic energy. Because
where does the kinetic energy come from? Because it's flow in the current, is it?
Because the electron has temperature. Remember we talked about temperature, and then we say that remember your kinetic model, when an object has a certain temperature, it will have certain kinetic energy. That means the particle will continue to vibrate about its position, it will continue to flow, it will slide past each other, or it will move randomly. Yeah, electrons behave somewhat like that. Okay, as long as they are at a certain temperature, then it will continue to flow because it has kinetic energy.
I still understand potential difference. Can I explain again?
So basically, potential difference is the difference in You know what's Jiayang, you know what's gravitational potential energy, right?
Yeah.
Okay, so can you see my mouse cursor?
Yeah.
Okay, we call this electron 1, okay? And then we call this electron 2. Is there a potential difference between electron 1 and electron 2 potential difference? Gravitational potential energy, sorry.
Yeah.
So there's a difference, right, in gravitational potential energy between electron 1 and electron 2. That potential energy difference, we call it potential difference in short. Okay?
Okay.
So in electricity, we don't use gravitational potential energy already because electrons are so light, it's somewhat not really affected by gravity. Okay, the amount of gravity that's affecting electron is negligible, but the amount of electric force that's like applying on an electron is not negligible. Okay, so what's happening here, right, is that the electrons are actually flowing, and as it uses up its energy, it goes downwards. Okay, in this illustration. Okay, so what's happening is that it's losing potential energy, just like how a ball loses potential energy when it's being thrown from a certain height downwards. Okay, Zhang, did I make myself clear, or you need explanation again?
Yeah, I think kind of.
Okay, so basically when you on a switch, okay, this entire thing will light up. Okay, the electrons will start to flow in this manner. Okay, maybe I play in slow-mo. Okay, so, this is the complex circuit. We'll talk about it later. Okay, can you ignore the word force and voltage for now? Okay, just ignore them. Okay, don't care about what they are talking about. All right. Basically, I just want you to see the animation of what I'm talking about. So the red color particles, they are basically your charges, and they are flowing. Okay, and as they use up the energy, okay, they actually flow downwards. Flow at the bottom platform. Alright, and as they gain energy, they'll go to the upper platform. Alright, so this entire platform, right, is the wire, and until they pass through a component, their energy stays the same. Okay, of course, that is not 100% true because wires are at most 99% efficient. Okay, that means what's happening is that it actually produces heat, and the heat actually causes the energy to be lost. Okay, but we assume no energy loss, and therefore the energy will always be the same, and the electrons will always be on the same platform. Okay, which is somewhat like this analogy. Alright, so at this point the electrons are flowing, okay, along the same height because it's not going through any component. Goes through a light bulb, goes down to a lower height, okay, goes along a wire, then goes through a light bulb, goes down a lower height again, then goes along the wire. Then you need a battery to push it up, and then it will come back here. Then the entire cycle repeats itself. Okay, you all clear about the idea of potential difference and current? yeah, I'm just going to add one. So this is the potential difference is basically the change in height of water. Okay, so actually I will stop here. This is the thing that I want to introduce to you all. Okay, I'm not going to go too deep today. Okay, yeah, so in class I will continue to build on what we learned today. Yeah, back in class I will continue to build on the idea of current first, and then we'll go into the idea of potential. Then I can talk about voltage and potential difference and this thing called electromotive force. Okay, which are all different, which are all basically pointing to the entire idea of this thing. Okay, but with different names. Yeah, and there's a reason why they are different names. Alright, anyone has any question? Can ask your questions now because I think I can end here today.
Sure, for midterms, this thing, how much will be done?
Yeah, apart from this kind of question, got any other question? Sorry, Zheng Yang, can't tell you. Yeah.
The charge always can be negative and positive.
If it's from electron, then the charge is negative lah. Right.
It's neutral.
No neutral, no. Neutral will be zero.
So zero charge.
Yeah, so like if you look at the charge, right, remember one electron is this amount, then one proton is this amount. If you add them up, you get zero. That's neutral. Right? You take the two circles, you add up, you get zero. That's neutral charge. Okay? Is this illustration?
Why you add them up? Why do you have to add them up?
If let's say in my atom I got one proton, one electron, then I add them up lah. Because one electron has this amount of charge, one proton has this amount of charge. So I add them up, you get 0 coulomb. Yeah, yeah. Everyone okay with this illustration?
I actually don't understand the potential difference.
Oh, Anik, don't understand potential difference. But okay. Anik, can you see that at point 1 the particle here has high GP?
Yeah.
Okay, so imagine it's just a ball. Okay, so if it's a ball rolling downwards, so as the ball rolls along the same height at here, okay, is there any change in GP? No. So at point 1 the ball has say 10 joules of GP. Okay, so let's say we talk about ball, and this ball has 10 joules of GP here. So as it continues rolling here, even when it's here, the GP is also 10 joules, right? Okay, so as it continues rolling down, and then it will roll, and then it will reach this point. So maybe at this point, the GP is 5 joules, right? Because it loses certain height. Okay, but I'm not in. Okay, while this is interesting, I'm more interested here. And then finally it rolls all the way down, and then we say that over here the GP is 0 joules. You agree?
Yeah.
Okay, so there's a loss in GP, right? Yeah, so the same idea is for the electrons or the charge. So imagine I represent one charge with a ball. Okay, so I will tell you that this is one charge, 1 coulomb of charge. Okay, and I tell you this is 10 volt. 10 volt will mean so remember the formula, V equals W over Q. So W equals to VQ, right? Which is 10 times 1, which is 10 joules. That means this ball has 10 joules of energy. This charge are not ball. Okay, so let me erase the working here. Okay, or if you want to see the working, it's like that now. Okay, so what I mean when I say this charge has 10 volts, okay, so assuming this is 1 coulomb of charge, what I'm trying to tell you is that this coulomb of charge here has 10 joules of energy, and as it goes through the wire, okay, it's not going to lose any energy. You only lose energy as it goes from this point downwards, as it passes through a bulb. So as it passes through a bulb, right, your bulb lights up, right? What's happening is that the coulomb of charge is actually transferring its energy to light energy, and then you suddenly see the light bulb lighting up. That's when energy is being used up. So the coulomb of charge will lose energy. So from 10 joules of energy, maybe it becomes 5 joules, and then it continues flowing along the wire. So this is still 5 joules, and then as it goes through another light bulb, okay, it becomes 0 joules. And that's the idea of volts. Okay, so basically voltage is about the energy level of the charge. Okay, so as the charge goes through a light bulb or any resistor or any electrical component, it's going to lose its energy, and you only get back its energy when it goes into the battery again. Okay, Anik, you okay?
Yeah.
Is it clearer?
The voltage is the current.
Huh? Voltage is the water flow. Here. Water flow. So the flow of this river is the same throughout. It's not going to change. Okay. Only the height at which the water is flowing is changing.
So we can only calculate potential difference as long as it goes through a component.
Yeah. So the potential difference across 2 points on a wire, right? Let's say I have a circuit like this. Y'all remember how to draw circuit, right? Y'all know how to read this? Yeah. Okay, so let's say, thanks Daniel, good question. So let's say I want to find the potential difference between these 2 points. What's the potential difference? 0 volt lah. Because it's the same, the potential difference is gonna be 0 volt. It's like taking this minus this. Now ask you what's the difference? 0 lah, right? Okay, but as it passes through the light bulb, it's gonna use some. Okay, that's when we actually get our potential difference, like a certain value. It's not gonna be 0. Okay, but same thing over here and here, the potential difference will be 0 volt also. Okay, because it's not passing through any electrical component.
Okay, so after it passes through like a light bulb, then it loses volts.
Yeah, it loses volts. More accurately, it loses energy, not loses volt.
So like for the thing you draw, then like once it passes through like the light bulb.
Here?
Then, yeah.
Okay.
Then like what's the potential difference? What's the difference?
So let's say the battery is 5 volt. 5 volt means that on flat ground, the battery is able to push the electrons up a certain height, like give it 5 joules of energy for every 1 coulomb. So that means along here, the potential is 5 volts. Okay, because the charges here, they are just moving along a flat ground. Okay, they have no change in height, so the potential should be the same. Whereas the potential here should be 0 volt, because over here is being used already. It's kind of like the video I showed you just now. Okay, so this is 5 volt. It's at a higher height, and then as it passes through the light bulb, okay, it's gonna use up its energy, and then it will be on the lower platform. And then as it flows, okay, so as it goes like that, and then as it flows back into the battery, it gets lifted up to the higher platform, and then it follows the red path. And then it passes through a light bulb, it goes down to the lower platform, then it follows the green path. Okay, so if I were to find the difference between, say, point A and point B, what is the difference?
Just minus
which is
5
volt. Okay, can. So if we call this point C and we call this point D, okay, what we can conclude is VAB is 5 volt, right? So the difference between A and B is 5. Now VAC, so the difference between A and C is 0. Okay, similarly, okay, VBD is equals to 0 volt also. Okay, because B is on the green path, D is also on the green path. As long as you're on the green path, your potential is 0 because your energy has been used up by the light bulb. Okay, because A and C are on the red path. As long as you're on the red path, your potential is 5 because no one is using your energy yet.
What happens if I put a light bulb at D?
Good question. Okay, so when you put a light bulb at D, right? Yeah. So this I'll be teaching you all this the next time we meet. Okay, so when you put a light bulb at D, you actually increase the resistance. Now when you increase the resistance, okay, the current will change, and when the current change, right, okay, what will change is that each light bulb will actually take lesser potential difference.
They will split it equally.
Yeah, it will split equally. That one we'll talk about in the next lesson. Let me introduce your resistance properly first. Yeah, so assuming that we don't add any light bulb. Yeah, so this is the basic understanding of potential. Alright, basically when you add an extra light bulb, right, you may actually do something like that. You may actually narrow the current flow. Okay, when you narrow the current flow, then things will start to change. Okay, but we don't go there yet now. Okay, we save that for the next lesson. Can Anik?
Okay, thank you.
Okay. Yeah. Because if I were to teach that, then I think maybe need another half an hour.
Wait, so for the resistance, right, you don't need to memorize the formula, right?
Resistance got one formula. If you want to know the formula, I can give you now.
Is it 1 over R equal to 1 over R1 plus 1 over R2?
No, that one is for calculation in a circuit. But the formula for resistance is this. R equals to V over I. So V equals to IR. If you want to memorize, you can. Okay, but I'll be teaching this again, so you don't have to write this down yet or now. Okay, you can write later.
So the formula to calculate the thing, do we need to remember?
The formula to calculate what? This
The 1 over R.
You need, yes. That one you will need to. Okay, if you want, you can try the question on page 7. Yeah, you can try the question on page 7. Then yeah, then I think we can call it a day. Alright, so let's try to apply the formula first. Okay, then if you are okay with page 7, I think yeah, you are free to go. Okay, maybe I just write the answer here. Should I write the answer here, or you all don't want to answer?
Okay.
Okay. Give you all 5 minutes. Page 7. Yeah. Okay, remember to change the minutes to seconds. So this is the answer. If anyone may go through any question, please either message me or like drop in the chat message here, or can then just voice
How to do 3 again?
3. How much energy, right? So it's about the work done, right? So remember the formula. Work done, voltage equals to work done per unit charge. So work done equals to VQ. Okay. Now Shelly, Vashini, Sen, Janelle, Jeline. Okay. If you all got question, please text me. Okay. Or you can just unmute and speak out.
How to do for
Sorry. How to do for?
Yeah.
Anyone want to share? What formula do you use here?
Q equals to IT.
Q equals to IT. So they want the amount of charge, right?
Yeah.
So current is 0.5. The time is 2 minutes. Now 2 minutes in seconds is 2 times 60. That will give me 60 coulomb. Okay. Now please take note. Over here they ask for the work done in 2 minutes. Okay. If they ask for 4, then your charge will change. Because this is the amount of charge in 2 minutes. Okay, so if I change the timing in part 2, okay, you cannot use the answer in part 1. You need to change the answer a bit. Okay, but anyway, they ask for the work done in 2 minutes, so you can just use the formula W equals to VQ. Okay, so then the volt is 12 and the amount of charge is 60, which will give me 720 joules. Alright.
Speak away if the question change like to 3 or 4 minutes.
For part 2, is it? So if let's say this is 4 minutes, so then remember the formula is W equals VQ. Now this Q, we need to ask ourselves Q in 4 minutes equals to
240 seconds.
Yeah, so we take Q equals to IT, which is the same current 0.5 times 240 seconds, which will give me 120 coulomb. So instead of using 60, I'll use 120. Can?
Okay. Yeah.
Okay. Otherwise, everyone okay? Question 1 and 2 also okay? Okay, since I already did all the working on myself, okay, so I equals to real flow charges, which is 30 over 120, which is 0.25. Okay. Okay.
Yeah, so volts is potential difference.
Sorry? Vote. Yes.
Yeah.
Yes.
Potential difference.
Yeah.
Oh. Thank you.
Okay. If you are okay with these 4 questions, I think it's good enough. Okay. Yes, Asa got a question.
Yeah, you know the one the graph, I mean not the graph, the diagram you draw just now.
The illustration.
Yeah, that one, the that one, yeah, that one. Is that conventional current?
Yeah, that one we will talk about in class. Yes, I'm drawing conventional current. Yeah.
Or that's why from positive to the negative terminal.
Yeah, correct.
Okay, can.
Okay. If not, I'll see you all soon. Okay, back in school. Okay. Yeah, get good rest tonight, everyone. Okay, good night. Bye.
Thank you, Mr. Go. Bye.
Thank you, Mr.
Bye.
Bye.
Thank you, Mr.
Got,
Bye.
got question ask, ah? Got question ask now, ah?
Mr. Go.
Yeah?
For potential difference when you measure it, does it necessarily have to be a bulk in the circuit?
Can be a resistor also.
And to measure potential difference, you use voltmeter.
Yes.
Oh, that one is for practical.
That one is for practical. No, that one is
We need to learn that in practical.
yeah, in practical we did it before, what?
Oh yeah.
Yeah.
Yeah, thank you.
Okay,
Bye-bye.
bye.
You.
Bye. Russ got question?
Oh, bye bye.
Okay, bye.